Hi, I'm Tuazon and I am here to discuss to you the circuit operation of an Astable Multivibrator. Presented here is the circuit for the Astable Multivibrator. So the Astable Multivibrator is a free-running multivibrator which has no stable states but has two quasi-stable states. The meaning of quasi-stable is that it seems or apparently but not really that the astable multivibrator has stable states, since its output would become high or low which has a given time period. So the circuit oscillates between Q1 on and Q2 off, or with Q2 on or Q1 off. Because of these two states, the output of each transistor has only two levels, which is from cutoff to saturation. So when the transistor is in cutoff, its output is approximately equal to VCC, and when it is at saturation, it is approximately equal to 0.2 volts. So because of these conditions, the circuit can be applied as a square wave generator. So to start with our analysis of this circuit, let us assume that Q1 is on while Q2 is off. So when Q1 is on, the base to emitter voltage of Q1 is at around 0.7 volts, while its collector to emitter voltage is around 0.2 volts. So for Q2, its collector to emitter voltage is around VCC. So while Q2 is off, it seems that as if Q2 is an open circuit. So the capacitor C1 has a direct connection to RC2 and to VCC, which means that upon power up of the circuit, C1 is charged to VCC minus VBE1. So now, when capacitor C1 is charged to around VCC minus VBE1, positive on the right side and negative on the left, VBE2's voltage now rises from below ground potential to about 0.7. So this is because that the base of Q2 has a direct connection from the supply through RB2. So when VBE2 rises from ground potential to around 0.7 volts, its collector to emitter voltage now becomes around 0.2 volts. So this is because Q2 is now turned on. So to simplify our discussion, let us assume that the collector to emitter voltage of Q2 is now shorted. So which means that it only has a 0 volt potential. So with that, it would seem that C1 is connected in parallel to the base of Q1 and to the emitter of Q1. So this voltage is now relative with respect to ground. So applying a negative bias towards Q1 would now make Q1 off. So Q1 would now have a voltage of around VCC for its collector to emitter, and the voltage of its base at that point would be now equal to VCC minus VBE1. So at this point, when the collector to emitter voltage of Q1 is around VCC, C2 then charges. So C2 charges because of its path RC1 and to the base of Q2 and to the ground. So the voltage that is charged to C2 is VCC minus VBE2. So with that, after the capacitor C1 has been discharged to around 0 volt, the capacitor C2 is now charged with VCC minus VBE2, positive on the left and negative on the right. The base emitter voltage of Q1 is now rising, since its voltage is also determined by C1. So it would be from VCC minus VBE1 up to the point about which is above ground at point equal to around 0.7 volts. So at this point, Q1 now turns on again. So with Q1 turning on, we can say that the collector to emitter of Q1 is now shorted, which then makes C2 in parallel with Q2's base and emitter. So with that, Q2 now turns off and its output would become again VCC. So to understand more about the astable multivibrator, I will present the waveforms for the astable multivibrator. So here represents the waveform for VBE1, for VCE1, for VBE2, and for VCE2. So the blue line represents the voltage at ground potential, which is 0 volt. So in the discussion, I have presented that we will assume that Q1 is on while Q2 is off at first. So when Q1 is on, its base emitter voltage is around 0.7 volts and its collector to emitter voltage is at about 0.2 volts. So at the same time, VBE2 is at ground potential while VCE2 is almost equal to VCC. So when the base emitter voltage of Q2 now rises to about 0.7 volts after capacitor C1 has been charged to VCC minus VBE1, VCE2 now turns on. So its voltage is now around at 0.2 volts. So at this same instant, the voltage between the base and emitter of Q1 is now equal to the voltage which is stored in the capacitor. So the voltage stored in the capacitor is around VCC minus VBE. So for these waveforms, we will assume that it is equal to around negative VCC. So at the same time, as Q1 turns off, its output becomes around VCC. So at this particular moment, the Q2 will still continue to be turned on, while since the base emitter of Q1 is now equal to the voltage across the capacitor, we will see that the capacitor discharges at this moment until it reaches a point which is above the ground, which is around 0.7. So at this point, Q1 now turns on again. And with that, the voltage between the base and emitter of Q2 becomes equal to the voltage of capacitor C2. So in this section, capacitor C2 is charged to around VCC minus VBE2. So to simplify, we will just assume that it is equal to around VCC. So its voltage to be which is plotted here is equal to around negative VCC. So at this instant, the collector to emitter voltage of Q2 rises up to VCC since it now operates into cutoff. So at this instant, Q1 remains to be turned on, while the base emitter voltage of Q2, which is now equal to capacitor C2 discharging, rises towards VCC, but it will just reach 0.7, which in turns Q2 on. So the voltage at this instant also capacitor C1 is charging to VCC minus VBE1 again. So we can see that the voltage between the emitter and the voltage between the base and the emitter of Q1 now becomes negative V at around negative VCC, and its output becomes at positive VCC. So upon continuous simulations of the waveforms, we can see that the astable multivibrator produces almost square wave patterns. So with that, the output could be retrieved from either collector emitter of Q1 or collector emitter of Q2. So this shows that the astable multivibrator is a square wave generator, and to add, these states are the quasi-stable states. So as I have said a while ago, a quasi-stable state is just seemingly but not really a stable state. So it could seem that from time t1 to time t2, this is the stable state of the multivibrator. Since it is quasi-stable, it would shift to around 0.2 volts at time t2 to time t3. So with that, I am now ending my discussion about astable multivibrators. Thank you.